Okay, I think we'll get started. So today we're going to introduce momentum and talk about conservation of momentum. And we've talked a bit about this early on, especially very early on when we talked about the conservation laws and the symmetries of nature. And this is captured by Noether's theorem. So Noether's theorem says that the invariant symmetry, time invariant symmetry, gives rise to conservation of energy, and space invariant symmetry gives rise to conservation of momentum, and then rotational invariance symmetry gives rise to conservation of angular momentum. So today we'll get the momentum piece. Now, momentum is defined as simply the mass times the velocity. And you'd say, well, why don't we just use the velocity? It doesn't seem like that big of a formula. But it really is because of Noether's theorem and what shows up there as momentum rather than velocity. So velocity is not necessarily conserved in some interaction, but momentum is. And so it's an important piece because of its conservation laws. Now, and whenever you have a conservation law, you have the ability to utilize those laws to help solve problems that might be otherwise pretty difficult. All right, so we've said that translational invariance gives rise to the conservation of momentum. So if we have a conservative or non-dissipative system, so there's no external forces, we don't have any drag or frictional forces that will lose that energy to heat, then the total momentum of that system is constant. So we could have any number of particles, Avogadro's number if we wanted to, in a container. And these particles are bumping into each other, bumping into the walls. The individual particles are changing their momentum. But the overall total momentum, if we were to add up the momentum vectors for all of these particles, then is constant. All right, so state that more specifically in math. So we will, before some kind of an event, and we'll be seeing collisions here very shortly, some kind of event, we have some initial momenta, and then we have final momenta after that event. And the conservation law specifically then states that the total momentum final minus the total momentum initial is zero. And so if it's not zero, then some kind of force had to act on this to change the total momentum. So this is if not acted on by an external force. Let's look at one little subtlety here with the harmonic oscillator. So in the harmonic oscillator, we usually draw a picture like this. And we say, oh, we can ignore friction, we can ignore drag, and it'll just go on forever. And that certainly would be a conservative system, but we have to be a little careful when we apply this conservation of momentum. Because notice, as this goes through its cycle here, it is obviously changing momentum, right? One time it's going this way, one time it's going this way, sometimes it's sitting still. And so our momentum will be positive, zero, negative. So what's going on here? Well, this is not the complete system. It's attached to this wall. And even though we're saying that wall is perfect, we're not letting any vibrations turn into heat and then dissipate the system, the wall still applies or mediates the force through the spring. So the spring's applying the force, but it's attached to the wall. And so the total system is what's in the box here, and we just don't see that wall move in a sense, although if the wall's attached to the earth and this little ball is vibrating on it, it is pulling that earth towards it as well. It's just not at all noticeable. So it's maybe a little easier to see if we have a dual mass system here. So two masses on a spring, otherwise completely free. So nothing else in its whole universe. These guys are just vibrating and doing so forever because there's no friction. And so at any point in this vibration, if this guy, say, is going this way and this guy is going this way, then in the center of mass system, the system that's moving along with the center of mass here, then the total momentum equals 0. And if the whole thing is moving, then the total momentum will just equal the momentum of the center of mass. Because as these vibrate, they're exactly canceling each other out. So whatever velocity this guy's going, so even if it's moving this way and they're going like this, as long as we account for that center of mass motion, then the deviation from the center of mass cancels out. And so a little easier to think about this system in this context than this system in this context. And just to kind of pick up a little something from the last lecture, now that we have momentum, we can easily translate that coordinate system or coordinate space to what is called phase space. And as you think about those diagrams that you drew for the coordinate space for the harmonic oscillator, all we would have to do then is multiply the velocity by mass, and we get momentum. So the position will still be the same, a, and then the mass will be m omega a squared. If we write out what omega is, then we can pull in a mass, so omega, so m omega is going to be m square root of k over m. So I can pull in an m squared k and then cancel out my mass and write it that way as well. This phase space is a little more fundamental because momentum is a bit more fundamental. And in advanced mechanics, which we'll get to in the curriculum, and in quantum mechanics, the connection between position and momentum is more directly gives us a way to explain the physics than position and velocity. All right, so that's it for conservation of momentum. So this is kind of a short video. We will apply it largely here now to collision problems, and it will help us solve some collision problems that would actually be pretty difficult.